Data Fusion and Qualification, Capstone project by John Blowers. The overall goal of this project was to develop next-generation, improved data fusion and data qualification capability for use with tracking systems out at White Sands Missile Range. White Sands Missile Range does a large amount of testing, and in order to provide their customers with the best deliverables possible, the tests need to be tracked. This tracking allows WSMR to be able to see and know what is happening at all parts of the mission, whether it's a single missile flying to hit a target, a rocket with maneuvering capabilities that homes in on its target, or a carrier missile that drops out 10 submunitions to blow up an entire area. The customer wants to know what happened and what it looked like. For this tracking, various instruments are used, including radars, optical tracking mounts, GPS, and telemetry systems. These sources provide measurements about the location of the target at different rates, with different latencies, and with different noise characteristics associated with them. The first block of my project fits in right here. To improve the tracking capabilities at White Sands, I needed a filtering block which would smooth, upsample, and remove latency from the input data streams. I utilized a Kalman filter to do the smoothing of the incoming data. Basically, through the use of this filter, I generated state estimates for each of the incoming data streams. These states included not only the smooth position of the target, but also gave me velocity and acceleration estimates. To get rid of the undersampled and delayed parts of the input from each sensor, I utilized the basic physics equations for position using velocity and acceleration. This combined with the state estimates gave me the ability to 1. Interpolate between measurements to effectively upsample to the master rate of 300 Hz, and 2. Predict ahead in time to remove that latency caused by data moving across the network. So now, I have data at 300 times per second, all synchronized to the same time step from each of the sensors in the mission. In the clip you're about to see, there are 3 tracks. The truth track, labeled panel 1, is completely smooth. The raw data track is labeled FPS 16, and the filtered has a lowercase f in front of its label. Here you can see the effects of the smoothing, upsampling, and latency removal done by my filtering block. The filtered output has significantly less jitter in this track than the raw data. It doesn't jump ahead and then pause like the raw does due to the undersampling, and you can see how it's been stepped ahead in time and is not delayed behind the ground truth like the raw track is. As I mentioned, the customer wants to know what is going on in the mission, but they generally have more interest in seeing certain parts of what's flying around. So obviously those objects of interest are of a higher importance to tracking than other objects of non-interest. So being able to distinguish what each sensor is actually tracking is quite valuable. This is my second block, qualification of the targets. To do this, I leveraged the state estimate information from the filtering block along with prior knowledge of what the specific mission was to involve to logically decide what each target might be. In this clip, the carrier missile flies out until a certain point where a deploy happens, at which point it kicks out 4 panels and 8 submunitions. The colors you will see correspond to what my qualifying block classifies each target as. Green is a submunition with no chute, dark blue is a panel, and cyan is a submunition with a chute. There's a certain period where the logic cannot determine exactly what the cluster of objects is, but as I separate more, it can pick up and start to distinguish between them, as you can see. The non-chuted submunitions hit the ground first, at which point they turn yellow to denote grounding. The other objects fall at a much slower rate due to the air resistance and the parachutes. You'll notice that some of the colors switch back and forth. This is due to the intrinsic noise in the sensors. The logic kind of gets confused when the noise gets in there and it switches back and forth, but overall it qualifies them all appropriately. Now you can see all the submunitions have hit the ground, and all that's left is the panels as they float down until they're finally all grounded and the mission is over. Now, with all these various sensors out in the field, there are times when some are locked onto the target really well and others are off tracking clouds or ground clutter or something else. My qualification gives grades to each of the sensor tracks based on how accurate they are, and these grades are then used to fuse the best tracks together using a weighted average in order to get an even better output track. This combination is my fusion block. In the next clip, you're going to see two videos side by side. The clip on the left shows all the sources that could be fused, and then the track of the fused output compared to the pre-mission simulation. The one on the right moves all the clutter from the left and just shows how closely the fused track matches the expected behavior of this mission. In this beginning part, you'll see some strange behavior. This is due to the transient behavior of the filters as they try to catch up in the beginning. But as it comes to this point, you can see the fused output matches right up with the pre-mission simulation and exactly how we would expect it to behave. The assignment block of my system deals with the distribution of the available sensors. For example, if we are looking at 3 targets of interest and there are 10 instruments, we don't want 6 instruments pointed at one target, 3 at another, and only 1 pointed at the last target. We want them evenly distributed, such that we have adequate coverage of all the targets of interest in the sky in that particular mission. This leads into the next and final block of my system, the visualization. White Sands has a software called RAGE that allows for the input of mission data and outputs an intuitive display of what was happening during that mission. This is what you've been seeing all the clips recorded from. This capability is very helpful because the outputs of all the other blocks in my system take the form of thousands of lines of data points that mean basically nothing to the human eye. In summary, my project takes in data from a variety of sources, filters it to smooth, upsample, and predicts to remove latency. It then qualifies the sensors based on logic about the state estimates to determine what is in the air. It takes confidence grades and fuses the higher accuracy tracks in order to have an even better output. It assigns sensors to distribute coverage in order to appropriately watch all the targets of interest in the sky. And finally, it allows for a user to watch and see exactly what the sensor inputs say happened during the mission. All of this together provides for improved data fusion and qualification capabilities for use with tracking systems at White Sands Missile Range. This is John Blowers saying thank you for watching and have a nice day.